Okay, so let's start. So today's topic is the semi-empirical mass formula. So this is a very important topic. In fact, we have to put several different pieces from the last couple of weeks together. Okay, so let's start it. So in the last few weeks, we talked about the basic nuclear properties, and then the champion is the binding energy, and we saw a couple of use of the binding energy. So we can use the binding energies to compute, straightforwardly, the mass of the nuclide. If you know the binding energy, then we can know the mass, or the other way around. If we know the mass, we can compute the binding energy. And the second use of the binding energy is to compute the Q value of the reaction, which is useful for both fission and fusion, and in fact also for radiological applications. So, and then we, okay, let me draw the figure first. So when we plot the binding energy per nucleon, so B over A versus A, we saw interesting behavior. For most of the nuclides, this B over A is a tiny band around 8 MeV. So most of them is around 8 MeV, except for those very heavy and very light nuclides. Okay, something like that. And for very light nuclides, we see some of those coming from the cell structure. Okay, but most of them are concentrated in this region of roughly in the range of between like 7.5 to 8.5 MeV. Okay. So if we just stop here, then every time if we need to use the binding energies, we can look it up in the chart of nuclide, which we can do, but it doesn't provide us much understanding. So the question, the follow-up question is, can we come up with a theory or something to describe this curve? If we do, then knowing the A, the mass number we want to compute, then we can estimate what is B over A. Okay. Of course, we have the very rough estimation, which is just a constant around 8 MeV. But can we understand a little bit more of this curve? Why does this curve bend down for heavier elements, or why there's a maximum near iron? And for the light elements, why do we have those oscillations that resembles the atomic structure we see in atomic physics, like the periodic table? So that is the focus for today. So the so-called semi-empirical formula is it's a semi-empirical because we're not going to derive this from the so-called first principles. The first principles usually refers to quantum mechanics because that is the very fundamental laws of physics. But some of the features we're going to describe on this curve indeed come from the quantum mechanics. But the other few actually come from our more empirical understanding of this curve related to like the size of the nucleus and the distributions of the mass and charge. Okay, so let's get started. So the semi-empirical mass formula, well, it's a mass formula, but as I mentioned, mass formula is equivalent to the binding energy. If you know the binding energy, then we know the mass. If you know the mass, we know the binding energy. Okay, so we usually write down this empirical formula in terms of B as a function of A. So we want to write down what is the binding, given a particular A, the mass number, then how do we compute the binding energy? So B is a function of A. Okay, so this B over A actually has a 5 terms. Let's go through each of them. So Let me write it down here. Let me leave a blank here. I'll have 5 terms, B over A. Let's explain them one by one. Okay. So the first one, the first term, is the volume term. Okay, why do we call this volume term? If you look at this curve, B over A, roughly B over A is a constant. Why is B over A is a constant? If B over A is constant, that means B is just directly proportional to A. So let's write this down. So B is proportional to A. And then the prefactor, let's call this A, small a, which is a coefficient. And add a subscript V here, indicate this is the volume term. So AV. So B is proportional A. Why is B proportional A? Because the binding energy, it's a total amount of energy that is released when we put our different nucleons together, or the other way around, the amount of energy that takes to tear the nucleus apart by separating all the nucleons from the nucleus to infinitely far away. Okay. So if the nucleons are banded together through a force, we don't really know the nature yet. But we know if B over A is a constant, then B is proportional to A. Okay. So this means the interaction of this nuclear forces, it's very short-ranged. So the binding energy of the amount of energy that is stored through this nuclear force is only proportional to the volume. And this is kind of understandable if you look at going back the density distribution of the nucleus. It's more or less uniform. So only at the very edge near the so-called skin layer, the density drops very sharply in the tiny region, roughly 1.2 Fermi. But other than that, the entire nucleus is uniform. So, and the nuclear force, or the force between nucleons, are only short range. In other words, nucleons only interact with its neighbors. So the total amount of energy is nothing but proportional to the total amount of matter inside the nucleus, or total amount of number of nuclei. So B is proportional to A. We see this comes from the fact that B over A, it's roughly a constant. Okay. So this implies that the nucleons only interact with their neighbors. In fact, not only interact, and we know this interacting is attraction. If it's without this retraction, if it's repulsion, then we wouldn't be able to fuse them together. So nucleons only attract their neighbors. Okay, so binding energy is proportional to the volume. It's proportional to A is the total mass number. Because of the density is roughly a constant, then the total mass number is proportional volume. That's why this first term is called the volume term. I think roughly speaking, it is straightforward. It's not trivial, but based on knowledge we have already known, this is straightforward. So the total amount of energy stored in nuclear is proportional to its volume. Right? And this is a consequence of the observation that nucleons only attract their neighbors. You think about if this is not the case, if nuclear force is like Coulomb force, pairwise, okay, and every nucleon interact with each other, then what's going to happen? Okay, so if all nucleons attract each other, if all nucleons attract each other, then what is going to happen? It was like the Coulomb force. Then we have to consider all the pairs, right? If we have a number of nucleons, then how many number of pairs we have is going to be a times a minus 1. So we choose 2 from A. So it's this. So then the binding energy, if the binding energy related to all the nucleons attracting each other, then this B would be proportional to not only A, but actually A times A minus 1. So that is not the case. So we know B over A is roughly a constant. So this is wrong. So that means the nucleons do not attract each other. Not all the nucleons attract each other. So the nucleons only attract their neighbors. Okay? So that's the first term. It's the volume term. The binding energy is proportional to the volume of the nucleus. Okay? And this term is really indeed the dominating contributions to this B over A curve. B is proportional to A. That's why for most of the elements, we have a roughly constant B over A. Okay. So, and all the other 5 terms can be considered as the corrections based on this very crude approximation. So this very crude approximation says the binding energy is proportional volume. Okay. And all the other terms are the corrections. So let's go through each of the corrections. So the first correction, or the second term, is still called the surface term. Okay. So in the previous model, when we consider total binding energy is proportional volume, we assume a uniform distribution of the nucleus, and every nucleon only interact with each other. But at the surface, the nucleons do not have as many neighbors as in the center. So outside the surface, there's nothing. So when we assume the binding energy is proportional to the overall volume, then we are overestimating the interaction or the energy needed for the nucleons at the surface. So we need to subtract that away. So we need to subtract a surface term away. Okay, and the coefficient is A sub S. It is the surface term, and and this term is proportional to the surface area. What is the surface area? And if A is total mass number, or proportional to volume, then if we assume the nucleus is just a perfect sphere, then the radius of the sphere will be proportional to the cubic root of A. Okay. So cubic root of A. Then the surface area will be proportional to the square of that. So because this bending energy is proportional to the radius square. Right? So the radius is proportional to the cubic root of A. And then we square that is 2/3. Okay, so we need to subtract this amount of energy away. So if you want to put more nucleons to the surface of a nucleus, then this nucleon doesn't interact with all of the surrounding nucleons, because outside the surface there's nothing. So I have to take that much amount of energy away. Okay, so that is the surface term. Now, if I draw another figure here on the right-hand side to B over A, so the first term will give us a B over A is a constant. Okay, so this is the volume term. Then we need to subtract this A to the 2/3 power term. Then what we end up getting will be something like this. So B versus A. Okay, we subtract the surface term. It's getting close to the experimental observation, but not completely yet. Okay, so this is the first correction based on the volume. And then the third correction is due to the Coulomb interactions. Previously, we completely ignored the Coulomb interaction. We assume that the protons do not even have charges. We didn't consider the interactions. And of course, the Coulomb interaction is much smaller than the nuclear interaction, but it's still there. And this effect is more and more important for heavier and heavier nuclei. So in those cases, we're going to have more and more protons, and then the amount of energies, the amount of repulsive energies is becoming larger and larger. Okay. So this Coulomb energy indeed is due to the Coulomb repulsions of the protons. So we have okay. So have the third term. So have to take away that amount of energy away. The coefficient, we call this AC. It's a Coulomb interaction. Okay. And Coulomb interaction is long range. Okay, so every proton is going to interact with all the protons inside the nucleus. And just like we argued in the volume term, if every particle interacting with all the others, then we have, in this case, we only consider the protons. So we have Z number of protons, and we pick two protons out of the protons. Then the amount of energy is proportional to Z squared, Z times Z minus 1. Okay, and then the distance, Coulomb energy is inverse proportional distance. And this distance, a natural unit will be just choose the radius of the nucleus. So the radius will proportional to A to the 1/3 power, so cubic root of A. Okay, so this is the Coulomb energy. And then this AC, so for all this AV, AS, AC, so there are prefactors with coefficients with a number. And for AV, let me write down the number. So AV is 15.835. Of course, all the units are MeV. Put the unit here. The unit is MeV. Okay, and a surface is 18.33. For AC, we know it's a small correction because the Coulomb interaction is much weaker than the strong nuclear force. So its AC should be a small number. In fact, it is a pretty small. It's 0.714. And among all these prefactors, this is the only one we can actually compute. Because what is AC? So AC ultimately comes from these self-energies when you put all these protons together, right? So if you consider the nucleus has a uniform charge distribution, which is the case as we measured before. So the charge distribution is more or less the same as the mass distribution. It's uniform. Then if a uniform charged particle with charge density described by like total charge divided by the volume. Then going back to classical, in this case, we don't even need the dynamic. In classical electrostatics, if we have uniformly charged sphere, with charge density rho, uniform distribution, then what is the Coulomb energy? So that can be computed easily. So by moving more and more charges to the center, and this prefactor is 3/5 of this E square over 4 pi epsilon naught times R. Okay. So the prefactor 3/5 that comes from the integral over the entire volume. And this number, in fact, we know all these numbers. R is 1.2 Fermi, and E is the charge of the electron, and so epsilon naught is the permeability of the vacuum. So put all these numbers in, and we see this is exactly 0.79 eV, very close to the empirical value. Okay, so put R to be 1.2 Fermi. Okay. So this is the third correction term. So this Coulomb term. And all these three terms, this AV, AS, AZ, comes from the simple assumption that the nucleus has this form of a sphere. And the sphere has a surface and has charge in it. So these three terms usually is referred as a model. This particular model of nucleus we call the liquid drop model. Let's put it here. So in other words, we consider the nucleus has this shape of a drop of a liquid. Okay, and the density of this liquid is almost constant. And that's why the amount of energy to put this liquid droplet together comes from these three terms: the volume, and it's overestimating. Then we take away the surface term. Then we take away the Coulomb interaction. Of course, the Coulomb interaction is a small correction. Okay, so even this is it's a very simple model, but it can already be very useful for us to understand this curve. Let me coming back here to draw what this curve looks like if you add the third term. The third term is proportional to z squared. So that means this effect is more and more for heavier and heavier elements. So then at third term, this curve will look like this. Okay. So now we have a maximum. Now we have a maximum here. Let me highlight maximum. Now we have a maximum. Okay, so the reason of this maximum, this B over A term, is because of, now we can see it comes from this Coulomb interactions. Without this Coulomb interactions, we won't have this maximum. Okay, so then you can already immediately see two important things we have already known in nuclear physics. Number one is why nucleus favors more neutrons than protons. If you remember, we plot all the known nuclei in this chart of nuclei, Z versus N, and we see many of them are lie below this line, Z equal to N. So in other words, we have more for most of the elements, the stable elements, we have more neutrons than protons. And this is actually because of Coulomb term. If we have more neutrons for the same A, even more neutrons, then the Coulomb repulsion is going to decrease the stability of the nuclei. Okay, in fact, we can do the calculations to find out what is this maximum location, but we can do that after we finish the last two terms. So let's get back to this highlighted region in a little bit. Okay, so then this is still not this semi-empirical formula with three terms still cannot account for all the observations we see experiments. And so we need to include more corrections. And these corrections come from the experimental fact for two important ones. One is so far we haven't distinguished the interaction between neutrons and protons, except this Coulomb's term. Okay, so and for most of the nucleus we know, roughly we have equal number amount of neutron protons, and because of this small correction here, this Coulomb interaction, then the nucleus favors slightly more neutrons and protons, but the majority of them are still equal to each other. So the fourth term, we need to account for this effect. We usually call that a symmetric effect, symmetric or asymmetric term. So that term, we need to penalize, because asym or asym. We penalize the nucleus with different number of n and z. So if n and z are the same, then they need to be maximize the binding energy. But if n and z are different, okay, take the n minus z square and normalize by this a. Now we need to penalize that. So in other words, for the same a, if the number of neutrons and number of protons are very different, and that is going to decrease the binding energy. Okay. So that is going to cause the instability. So that this term doesn't come from the liquid drop model. Like liquid drop model does not distinguish neutrons from protons. In fact, this term is much more subtle, and the underlying reason why this binding energy is related to this comes from a more rigorous calculations of nuclear model. In fact, the last term as well, so they come from the shell model. Okay. So this term and the last term comes from the shell model, and the shell model is the focus of the next couple of lectures. So, and that is obtained from quantum mechanics. In fact, you can already see, without getting into the details, you can already see, like when we put a particle in the infinite square well potential, then we see the energy split into multiple different levels. In 3D, then those different energy levels are called different shells. Okay? So the energies of neutron protons are quantized, occupy different energy levels. And then the reason we have this term proportion n minus z squared comes from the fact that we need to fill in those energy levels from the lowest energy to highest energy, and fill all the way so-called to the so-called Fermi level. Then, so this feeding of the different energy levels will cause binding energies related to this n minus z squared term. Okay. So let me leave one comment here, but because of this term, for most of the stable nuclei, then we have n is proportional to z. Right? If n is not the same as z, then this term is going to penalize binding energy or cause the instability of the nuclei. And the larger difference between a and z, n and z, and the lower the binding energy, so it means the less stable the nuclei is. Okay. So this term will favor an approximately the same as z. And for this term and the previous term together, Coulomb term together, so the Coulomb term will add a slightly a slight bias to this n and z balance, and favor slightly more, because this AC is a very small number, it favors slightly more neutrons than protons. Okay, so indeed, if we put these two terms together, it comes back to the point that I missed here. So number two, because Coulomb interaction and asymmetric terms, then we have a maximum binding energy, maximum B over A at roughly A equals 60, okay, which is the ion position. So, well, in fact, now with this formula, we can compute that. So we have B as a function of C. Then you can take the derivative. We can take the derivative and then find out where this maximum is. Okay. So the reason we have this maximum near the iron location is because of combination of two things. One is the stable nuclei will favor N is approximately the same as Z. And two, it's really due to the Coulomb repulsion. So for elements, for nuclei with a mass number more than ion, then the amount of protons inside the nucleus will cause the nucleus to be less stable. So that is essentially the insight. So for the elements lighter than ion, then we can still fuse them together and to release energy. So the Coulomb interaction essentially is still negligible. So the balance between the Coulomb interaction and nuclear force is really at the iron location. Okay, we'll have more protons later on for the heavier nucleus. Then the Coulomb energy is going to cause the nuclei to be less stable. Like for example, like take uranium example. Then by splitting this nucleus into different fragments, it's going to release energy. So that is the physical meaning of why we have maximum near the iron location. Okay, so the last term of this correction, okay, actually, by the way, let me write it down. What is this ASIM term? So this ASIM is roughly 23.20. So the last term, again, comes from the nuclear shell model, but counts for one important observation we mentioned last time, this odd-even effect. So remember when we consider the separation energy of the last neutron or the last proton, okay, so which is also equivalent to like the amount of energy that gets released when we put the last neutron protons to form this nucleus. So that number depends on whether we have even number of nucleons or odd number of nucleons, or neutrons or protons. So we mentioned that the experimental observation told us, so for nuclei with even number of neutrons and even number of protons, it is much harder to take away or separate one neutron, one proton from the nuclei. So neutrons and protons tend to form pairs. So that's called the obvious odd-even effect in the separation energy. So that term should also be reflected in the expanding energy. So depending on whether even number of neutrons or even number of protons, then when they are even, expanding energy should be more, right? It means the nuclei are more stable. So the last term indeed is this odd-even term, or called pair term, so called AP. Okay, so this term, okay, I think here, so it's AP, or precisely inverse proportional square root of A. Okay, so it's AP term, and this parity AP is not always positive. So it depends on whether we have even or odd number of protons. So in fact, when this term doesn't need to be there. If N and Z is one of them is even or one of them is odd. So if N and Z, so N and Z, so if one of them is even, so one even, one odd. So one even, one odd. Okay, then we don't have to penalize the binding energy. But if N and Z are odd, so if N and Z, if both of them are odd, okay, so odd, and we know the nucleus is not stable, right? For odd configurations, it's not stable, then we need to put in more binding, we should take away more binding energy, so we have a negative term. So this value is negative 11.2. Okay. And for N and Z are even numbers, have an even configuration, then the nucleus is more stable. So that means we need to have more binding energy. And this is a positive term, positive 11.2. Okay. So this last term really accounts for the odd-even effect. So even configurations are the most stable configurations of a nuclei. Okay. So this last term, this last correction term, so a P term, comes from this odd-even effect. Okay. So those are the 5 terms to describe this B array. And then when we put all these 5 terms together, so I didn't draw the last two, this asymmetric term will have a slight more multiplication of this curve, and then odd even will shift this curve up and down, depend on even odd configurations. And now this last curve, maybe I should draw it with a different color. Use a different color. So this last curve, okay, is indeed very close to the empirical, the experimental observations. In fact, for most of the nuclei, the accuracy is better than 1%. Okay. So now with all these numbers, AB, AS, AC, ASIM, and AP, then we don't even need to go back to the chart of nuclei. You can use the simple semi-empirical formula to estimate the binding energy of the nuclei. Okay. So of course, this is not exact for all of them. The discrepancy is larger when the shell model, this quantum mechanical effect, is more important. In fact, especially for those light elements, when we have all these oscillations, like for helium, for boron. So like for these light elements, then the binding energy per nucleon is deviating from this curve more. But those are simpler nuclei, and we can explain them from quantum mechanics directly. Okay, so this is the so-called the semi-empirical force formula. And so now since we have the entire curve B over A, then you can take derivative to find out what is this maximum. So we need to take a B, well, this is a B as a function of A. So first we need to divide it by A, so B divided by A. Then we take the partial derivative, and set it to be 0. Then we can find out this maximum. And that give us the location of close to I. So A is roughly 60. Okay. So this is the binding, this semi-empirical formula for the binding energy. So now a topic close related to this. What can we do with this semi-empirical formula? If we know B as a function of A, if you think about what is the definition of the binding energy. So binding energy B as a function of AZ is equal to, so we have a Z number of hydrogen or proton plus N number of neutron, and then take away the mass of this AZ element, and then times C squared. And then times C squared. So the mass of hydrogen and mass of neutrons are known numbers. Then if we know the binding energy, then we know the mass. So the other way to make use of this is to directly write down the mass. This leads to so-called mass parabola. Parabola. Okay, why is it called parabola? Let's write it down. So then what is the mass? So mass of AZ, let's write this down, mass in terms of binding energy. So that be equal to, so Z number times the mass of hydrogen plus N times the mass of neutrons, then minus, so the binding energy divided by C squared. So if we know the binding energy, then we can plug it in here, then we can know the mass. So in particular, for given A, if you plot this mass versus Z, okay, for a given A, then let's see what do we have. For given A, what do we call them? For the nucleus with the same A, we call them isobars. Right? So this is, consider a sequence of isobars for the same A. Okay. Then this binding energy will allow us to examine the stability of the nucleus along this isobar. Okay. Now what is B? We don't have to write it down explicitly. If you want, we can, because B as function AZ is already known. If you're going back here, now we want to plot this B as a function of Z. So first term is a function of A, the second term is function of A. So we consider B as a function of Z for given A, like the first two terms are just constant. Third term is where the things become interesting. So third term proportional Z squared. And fourth term also proportional Z squared. And the last term is the odd even correction. So overall, B over A is a parabola. So B is a proportional to Z squared. We'll also have linear terms, where the highest order is Z squared. So B over B as a function of Z is a parabola. Then if you put in this equation, the first term is proportional to Z, so still a linear term. And the second term is constant. So overall, this shape is a parabola. Okay, so that's why we call this is the mass parabola. So for given A, if you plot the mass as a function of Z, we're gonna get a parabola. And well, that depends on this parabola. Depends on the odd even number. So if A is an odd number, let's draw this. If A is an odd number, if odd A, if A is an odd number, then N and Z must be even and odd. Right? One of them must be even, the other must be odd, so that they add up together to be odd number A. In this case, we don't need any corrections. So without correction term, then this is easy. We can draw this mass as a function of Z. So draw this mass as a function of Z. So this axis is the Z. Okay. Because parabola has this shape. So here on this curve, we can find multiple nuclei. We can find multiple nuclei along the same isobar. So now the same A, same isobar. Then now we can take the derivative. So we can take the derivative, find out the most stable, or the lower the mass, and the smaller the mass, that means the more stable this nuclei is. So we can take partial M, partial Z, and let it to be 0. And we have mass as a function of Z to be parabola, so partial M, partial Z. And then we can find out where is this minimum. So the minimum, a lot of terms are constant, which can go away. Then this is the answer. So 1 plus 1/4 AC, the Coulomb term, divided by the asymmetry term, and times A to the 2/3. Okay. So we can immediately reach this conclusion. So for smaller a, like for small a, then this a to the 2/3 power term is essentially 0. Okay, AC is a small number anyway. So then this Z mean is approximately just half of A. And this is null. Remember, for the same isobars, then the most stable nucleus is indeed when you equally split, roughly equally split. This is out a roughly equally split neutron and protons. So most of the elements are roughly around this n equal to z line for small a. And for large a, for the slightly heavier elements, then it's the mean, which is not just 1/2, because we have this denominator here, which is more than 1, then the mean will be slightly less than a over 2. So number of protons is less than half of the total mass number. So that explains the deviation from this z equal to n line for heavier nucleus. Okay, and in fact, for most of them, this is roughly 0.4 of like 40%. 40% of the nucleons are protons, 60% of neutrons. And you can see why this is the case. Indeed, this deviation from z equal n comes from this combination of AC term and asymmetry term. It's really a balance between the Coulomb interactions and the symmetry terms. Okay, and so the closer to the minimum, the more stable the nucleus is. If you have if we start from something like, say, some nucleus here, then it is less stable than the one at the bottom. So the nucleus can undergo radioactive decay and go to the most stable one. So from the left-hand side, now the Z is increasing. So this process is the beta decay. For the neutrons, for Z decrease, so for the neutrons to disintegrate and release the electrons, beta decay, and convert, basically you convert one neutrons to one proton and increase the Z number. And for, so because left-hand side are this neutron, this is a neutron-rich neutron-rich nuclides for this isobar. And for the right-hand side, well, proton-rich. For proton-rich nuclides, they can undergo the beta plus decay by giving out a positron, and then eventually go to the minimum. Okay. So either this is either beta class decay, or another mechanism will be the electron capture. So the protons inside nucleus can also capture the electron and then decrease the converted proton into neutron and decrease the charge by 1. So this process can happen, electron capture can happen. It's also because of like electron is not just one particle, it's a wave. And the wave can go from 0 to infinity. So the electron always have some non-zero time that they can spend inside the nucleus. And that's why the protons can capture them and then create a hole inside the electron cell. But then other electrons can hop in and release another energy that's counted by another photon, which can be detected. So, but overall, the important thing is when we convert protons and neutrons, depending on whether the nucleus is neutron-rich or proton-rich, they can go to this most stable nucleus. So if we have a even A, so the other scenario, if we have even A, then we can have two problems. One of them is even. So we have even number of N, even number of Z, and the other is odd. Okay, drop 2. In fact, the even one would have smaller mass because they're more stable. And the odd ones are the odd. What I mean by even and odd is the number of neutrons and number of protons. So the odd configurations will have slightly larger mass. And the difference of the two, right? The difference of the two is known. It's just related to this 2 times this AP term divided by square root of A. Okay. So, and then again, we can have multiple elements or nuclei on these two curves, and then we can, like, if for proton-rich nucleus, they can undergo either the beta plus decay or electron capture to convert one proton to a neutron, or the other way around. If we have a more neutron, the neutron can decay to protons to create more Z through this beta decay process. Okay. So a lot of radioactive decay really comes from this binding energy, and it comes from this empirical formula. One very interesting, just last thing before I let you to go, it's like if you consider this one, this nuclei, it can undergo a beta decay, but then it hops to this odd configuration, not that stable as before. And this odd nucleus can keep undergo another beta decay to here. So when that happens, directly this nucleus can go from here to here by giving out 2 electrons, because now I'm plotting as a function of Z, so Z increases by 2. And this phenomenon is so-called double beta decay. So this can happen sometime. So for some unstable nuclei, they can give out 2 electrons and then goes to a state with lower mass. Okay. So bottom line is a lot of the nuclear phenomenon can already be understood with such a simple model. And we can, going back here, it's this semi-empirical mass formula. The first part comes from the liquid drop model. The last two come from the correction from the nuclear shell model. Okay, so time is up, and I think I'm gonna stop here today. This is a very important topic. I hope you can spend some time to think about it. Okay, we'll see you on Wednesday.
Thank you, Professor.
Thank you.